Hello everybody. Today we will discuss problems from US Physics Olympiad 2007. First round, it's called F equal AM. There will be 38 problems, not very hard, I would say middle level problems. So you just need to solve these problems for a certain time. Usually it takes for 25 problems it takes about 75 minutes to solve, but for this year it was 38 problems. And yes, usually they're giving you 5 different options for answer, and you need to solve and check which one is correct, like this. That's it. Problem number 1. An object moves in 2 dimensions according to equation representing here, where r is in meters and t in seconds. When does the object cross the x-axis? On the left side we have 5 options to choose correct one. And in this kind of problems we need to understand that we have very short time for many problems, and we need to solve them these problems quickly. So we just need to understand that crossing the x-axis, it means that this part is equal to 0. From here we can find that time t equal 2.5 seconds. And this is the solution, this one. Problem number 2. The graph shows velocity as a function of time for a car. What was the acceleration at the time 90 seconds? As we know, to find what is the acceleration in representing moment, we just need to find what is the slope for this curve in this point. So to count what is the slope in point 90 seconds, we can just draw the line between this point 60 seconds and 120 seconds, and find what is the slope. Because on the left side we have 5 options, and we see that they are very different from each other, so we don't need to count it precisely. So acceleration must be equal to 30 minus 10 meters per second divided by time difference, which is 60 seconds. So the answer is 0.33 meters per second square. So we see that the correct answer is B. Problem number 4. An object is released from rest and falls a distance h during the first second of time. How far will it fall during the next second of time? We know that object moving with a constant acceleration, it moves like parabola, but when it's moving from rest, the formula is h equal 1/2 g t square, which is quadratic to time. So it means that if we need to count what distance it travels during the same period of times, it raises as arithmetic progression. So if it's going for the first second, it's going for distance h. Next second will be 3h. Third second will be 5h, etc. You can find it using this formula. So it means that correct answer is C, 3h. Problem number 5. A crate of toys remains at rest on a sled as the sled is pulled up a hill with an increasing speed. The crate is not fastened down to the sled. What force is responsible for the crate's increase in speed up the hill? And we have several options, 5 options for answer. First option, the force of static friction of a sled on the crate. So this one between this sled and this crate. The contact force, normal force of the ground on the sled. It means that from this plane, not from ground, I believe. The contact for normal force of the sled on the crate. So normal force from this sled on this crate. Number D, gravitational force acting on sled. Okay, gravitation force on the sled. And E, no force is needed. So the answer we can find from, if we draw a free body diagram on this crate, which is force of static friction, normal force from sled, and gravitational force from Earth. So if we can see, normal force is not responsible for acceleration, and we just cancelled this part of gravity force. And honestly, the interaction between static friction and this part of gravitational force responsible, but gravitational force is acting opposite to acceleration, so we can choose the answer A, where the force of static friction of the sled on the crate. So probably that's correct answer. I would say this problem is not very correct formulated. Problem number 8. When two stars are very far apart, their gravitational potential energy is 0. It's a regular assumption for potential energy in gravity forces. When they are separated by distance d, the gravitational potential energy is U of all this system. If the stars are separated by distance 2d, so what is potential energy? We just need to write the expression for potential energy. That's equal negative G m1 m2 over d. That's the first case. Second case, we are increasing distance 2 times, so we have U2 equal negative G m1 m2 over 2d. And we see that in second case potential energy twice less than in first case. So the answer is this one. Problem number 9. A large wedge rests on a horizontal frictionless surface as shown. A block starts from rest and slides down the inclined surface of the wedge, which is rough. So we have friction between these two objects. During the motion of the block, the center of mass of the block and wedge moves somehow, and we need to move to find how it will move. So we have 5 options. First option does not move. Second option moves horizontally with increasing speed, with constant speed. I'm sorry. C moves horizontally with increasing speed. D moves vertically with increasing speed. And E moves horizontally and vertically. So first we can conclude from this problem that this surface is smooth. There are no friction between surface and this wedge. It means that we don't have any force, horizontal force on this system, and it means that we don't have any horizontal acceleration. So it means that if center of mass of this system was in rest, it will stay in rest and after beginning of motion. Next one, because we have motion, it means that this block moving to the left and this wedge moving to the right. It means that center of mass of this wedge not moving vertically, but this will move vertically. It means that common center of mass, whole system moving vertically down with increasing speed, moving with acceleration. So that's the answer. We don't have any motion horizontally for center of mass. It stay and it moving vertically with increasing speed. So the answer is D. Moves vertically with increasing speed. Problem number 10. 2 wheels with fixed hubs, each having a mass of 1 kilogram, starts from rest, and the forces are applied as shown. F1 this way, F2 this way. Assume the hubs are spokes. The hubs and the spokes are massless, so that we can count rotational inertia I equal mr square. In order to impact the identical angular accelerations about their respective hubs, how large must be F2? So we can use this rotational formula for angular acceleration. That's I alpha equal to Fr, and if we use expression for I is mr square, that will be mr square equal Fr. So from here we can find what is the I forgot alpha. So from here we can find what is alpha. That will be alpha equal F over mr. So to get the same angular acceleration, we just need to increase force twice if we increase radius twice. So the answer is 2n. Problem number 11. A uniform disk, a thin hoop and a uniform sphere, all with the same mass and the same outer radius, are each free to rotate about the fixed axis through its center. Assume the hoop is connected to the rotational axis by light spokes. with the objects starting from rest, identical forces are simultaneously applied to the rims as shown. Rank the objects according to their kinetic energy after a given time t from rest to greatest. So all three objects are in the same condition, so we can just compare their final kinetic energy. So kinetic energy equal 1/2 I omega square. So we need to find what is expression for this kinetic energy. So to find what is omega, that's angular acceleration multiplied by time. And the angular acceleration we can find from regular expression I alpha equal Fr. So it means that alpha equal Fr over I, omega equal Frt over I, and finally kinetic energy equal 1/2 I F square R square F square R square T square over I square. So one time I is cancelled, and we have kinetic energy equal 1/2. Same expression for all of them on the top, and on the bottom we have different I. So we have for greatest moment of inertia we have least energy. So it means that correct answer will be, we know that for disk we have I disk equal 1/2 m r square. For hoop we have that's m r square, and for sphere we have I sphere equal 2/5 m r square. So the least I is for sphere, for greatest I for hoop, and this in the middle. So it means that for sphere we have for hoop we have least, for disk that's next one, and for sphere we have greatest kinetic energy. So that's the correct answer. Problem number 12. A 2 kilogram rock is suspended by a massless string from one end of the uniform 1 meter measuring stick. What is the mass of the measuring stick if it is balanced by a support force at the 0.2 meter mark? To solve this problem we need to write equation for static equilibrium. So for this we need to write torque from the left, which is mg by 2.0 meter, and that's equal unknown mass m g multiplied by distance from center of gravity for this stick, which is right in the middle of the stick. So it means that this distance is 0.3 meters. So to calculate what is total mass m, big one, that will be m2/3, which is 1.33 kilogram. So from here we have C, correct answer. Problem number 13. A particle moves along the x-axis. It collides elastically head-on with an identical particle initially at rest. Which of the following graphs could illustrate the momentum of each particle as a function of time? We know that during absolutely elastic collision of two identical particles in one dimension, 1D, they after collision they will exchange momentums. So it means that first particle moves and after it stops, and after collision second particle start to move with the same momentum as momentum of the first particle before collision. If we check all graphs, we can see that only on graph D we have this situation. Second particle not moving, first particle has impulse P, momentum P. After short collision, second particle move with the same momentum as the first particle before collision, and the first particle just stop. So D is correct answer. Problem number 14. When the speed of a rear drive car is increasing on a horizontal road, the direction of the frictional force on the tires is next one. So we have car, and this car is moving to right with increasing speed. So it means that we have acceleration to the right, and for rear drive car it means that rear wheel will supposed to create force to move forward this car with the acceleration. So it means that force of friction from this move is going to the right. And the other wheel, which is a forward wheel, it's moving without, it's not connected to engine, so it's moving free. So it means that force of friction going to the left, it's going to opposite direction to the motion. So that's correct answer. If we check all 5 answers, that will be A. Problem number 15. A uniform disk with a moment of inertia 1/2 mr square of mass 8 kilogram can rotate without friction on fixed axis. It's here. A string is wrapped around its circumference and is attached to a 6 kilogram mass, this one. The string does not slip. What is the tension in the cord while the mass is falling? So to solve this problem we need to write equations for motion for both bodies, for small mass m and for this disk m, rotation. This is for motion, this is for rotation. For mass m, equation is this one. ma equal mg minus tension. And for disk we have rotation, we have I alpha equal tension multiplied by radius. So because we don't have slipping of this cord, we have alpha equal AR. So this is how to connect angular acceleration to linear acceleration. And we can put this expression here, and for moment of inertia this one. So instead of this equation we have 1/2 m r square multiplied by a over r equal TR. And we can cancel radius as regular in such kind of problems, and we have tension equal 1/2 MA. So we can put this tension in the first equation, and we can find MA equal mg minus 1/2 MA, and from this equation we can find what is acceleration. That's equal mg over m plus 1/2 big M. So which is 6 over 10. So that's 0.6 g. And when we found what is acceleration, we can put this acceleration in this expression for tension. This is what we need to find. That's 1/2 8 multiplied by 0.610. So that will be 24 newtons. So that's correct answer. B is correct answer. Problem number 16. A basketball is dropped on top of a baseball is dropped on top of a basketball. The basketball hits the ground, rebounds with the speed of 4 meters per second. And collides with the baseball as it moving downward at the same speed, 4 meters per second. We choose up direction is positive. So it means that initial speed of baseball is negative. After the collision, the baseball moves upward as shown in the picture, and the baseball is instantaneously at rest right after the collision. The mass of baseball is 0.2 kilogram and mass of basketball is 0.5 kilogram. Ignore resistance and ignore any changes in velocities due to gravity during the very short collision times. The speed of the baseball right after colliding with the upward moving basketball is what? So here of course we need to use equation for momentum conservation during collision. Before collision we had momentum for basketball is m2 v2 and momentum for baseball is m1 v1, and after collision baseball is stopped, so its momentum is 0, and momentum for baseball is m1 v. So from this equation we can find what is speed of baseball right after collision. So we have 0.5 multiplied by 4, and here we have negative 0.2 multiplied by 4. So the speed is velocity of this baseball is negative, and that's equal to 0.2 v. So from this equation we can find that speed v equal 6.0 meters per second, which is correct answer. Problem number 17. A small point-like object is thrown horizontally off a 50 meters high building with an initial speed of 10 meters per second. At any point along the trajectory there is an acceleration component tangential to the trajectory and an acceleration component perpendicular to the trajectory. How many seconds after the object is thrown is the tangential component of the acceleration of the object equal to twice the perpendicular component of the acceleration of the object? Ignore air resistance. In any point we can split our acceleration g for two components. One is tangential gt and other is normal g normal. What does it mean that tangential component is twice as normal component? It means that the tangent of this angle, tangent theta, equal 1/2. So there is a relation gn over gt, it's 1/2. That's from one hand. From other hand, we have speed, we have velocity, and the velocity we can split for horizontal and vertical component. And for such split, tangent of this angle equal to Vx over Vy. So that will be Vx over Vy, which is again equal 1/2. Vx is constant and Vy equal gt. So from here we can see that Vy equal 20 meters per second. It means that time equal just 2 seconds. The last step is we need to take into account that we have enough time for such moment. So we need to check if our total height less than 50 meters. So we can find that y equal 1/2 gt square, which is equal 1/2 10 and 2 square, which is 4. So total is 20 meters, which is good enough for 50 meters high building. If we look at answers, we have 2 seconds, and the last thing is the building is not high enough for this occur, so that this is not the case. So correct answer is 2 seconds. Problem number 18. A small chunk of ice falls from rest down a frictionless parabolic ice sheet, like here on the figure. At the point A in the diagram, the ice sheet becomes a steady rough incline of angle 30 degrees with respect to the horizontal and the friction coefficient mu, unknown coefficient. This incline is of length 3/2h. h is initial height. The chunk of ice comes to rest precisely at the end of this incline. So what is the coefficient of friction, mu? So in this problem, the best way to do is to use work energy theorem. So it means that our potential energy initially go into kinetic energy for this chunk, but because it's come to rest in the end, it means that all this energy will spend for friction, for work of force of friction. So we need to just to write this equation. Potential energy, which is mgh, that's equal force of friction multiplied by length, which is 3/2h. So force of friction equal we know it's a coefficient of friction multiplied by normal force, and normal force equal mg multiplied by cosine 30 degrees. So when we put all these meanings here, we can get final equation mgh equal mu mg cosine 30 degrees by 3/2h. So we have mgh cancelled, and finally we have mu equal 2/3 1 cosine 30 degrees. Cosine 30 degrees is √3/2, so we have finally 4/3√3. So we can use calculator, and the answer is B, 0.77. This is the correct answer. Problem number 19. A non-Hawkian spring has force like this. So we see it's not proportional to a displacement, it's proportional to quadratic to displacement, where k is the spring constant and x is the displacement from its unstretched position. For the system shown of mass m connected to an unstretched spring initially at rest, how far does the spring extend before the system momentarily comes to rest? Assume that all surfaces are frictionless and that the pulley is frictionless as well. So angle is 30 degrees, and to solve this problem we need to use energy work theorem. It means that whole potential energy for this mass during after its stop, it will go to potential energy of this spring. So potential energy, if we have total displacement is x, so total potential energy will be mgx multiplied by sine 30 degrees. And that's equal to potential energy of the spring. We know that for regular Hawkian spring we have potential energy equal 1/2 kx square, but in our case we need to do integration, because if we have graph force as a function of displacement, in our case is parabola. So to find what is total energy, we need to count what is the area under this curve, which is integral. And I can remind you what is the integral from polynomial. If we have polynomial function like x power n dx, integral will be 1/n plus 1 x power n plus 1. In our case n equals 3, so we can say that integral from kx square from 0 to x dx, that's equal 1/3 kx cube. And this expression we can put here, 1/3 kx cube. So we see that sine 30 degrees is 1/2. 1 time x is cancelled. We have here x square, and after simple calculation we can find that x equal this expression a. So this is solution. Problem number 20. A point like mass moves horizontally between two walls on a frictionless surface with the initial kinetic energy E. With every collision with the walls, the mass loses 1/2 of its energy to thermal energy. How many collisions with the walls are necessary before the speed of the mass is reduced by factor 8? So V is reducing to 1/8. To solve this problem we need to write expression for kinetic energy. That's 1/2 mv square. So we see that if speed reduces 8 times, it means that kinetic energy reduces 64 times. So we have kinetic energy going to factor 1/64. But we know that after each collision we're losing 1/2 energy. So we just need to equalize this 1/64 to 1/2 power n, number of collisions. So it means that we have 2 power n equal 64 and n equals 6. So this is correct answer, C. Problem number 21. If the rotational inertia of a sphere about an axis through the center of the sphere is I, what is the rotational inertia of another sphere that is the same density but has twice the radius? So we just increase radius twice. We know that for solid sphere we have rotational inertia, it's 2/5 mr square. But suppose we forgot this coefficient in this problem, we don't need this. So it's like beta mr square. So to solve this problem we need to count what is the new mass and put this new radius. If we increase radius twice with the same density, we increase volume 8 times. It means that mass will increase in 8 times. So we have I prime equal beta by 8 mass and the 2 radius square. So which is 32 times beta mr square, which is 32I. So that's our correct answer. Problem number 22. 2 rockets are in space in a neglectable gravitational field. All observations are made by an observer in a reference frame in which both rockets are initially at rest. The masses of rockets are m and 9m. A constant force F acts on rocket of mass m for a distance d. As a result, the rocket acquires a momentum p. If the same constant force F acts on the rocket of mass 9m for the same distance d, how much momentum does the rocket of mass 9m acquire? So we need to find what is p prime. So to solve this problem we need to check that if a force acts, same force acts on the same distance, it means that both rockets they are getting the same kinetic energy, and the kinetic energy has this expression 1/2 v square, which we can write through momentum p square over m. From this we can find that momentum equal root 2km, and if we look to this expression, kinetic energy is the same, but mass was increased 9 times. It means that momentum was increased 3 times. So D is the correct answer. Problem number 23. If a planet of radius r spins with the angular velocity omega about an axis through the North Pole, what is the ratio of the normal force experienced by a person at the equator to that experienced by a person at the North Pole? Assume a constant gravitational field G and that both people are stationary relative to the planet and are at sea level. And assume they have, of course, the same mass. It's obvious that on North Pole we have a normal force equal to gravity force, because this person is not moving, it's stationary. So we have normal force equal mg. On equator, person going by circular trajectory, and we know that in this case we have centripetal acceleration with a centripetal force equal mr omega square, and if we have normal force N and gravity force mg, so we can say that this force is a result of N and mg. So we have mg minus normal force equal r mr omega square. So from here we can find that normal force equal mg minus mr omega square, and we have n over mg equal 1 minus r omega square over g. So that's correct answer, which is C. Problem number 24. A ball of mass m is launched into air. Ignore air resistance, but assume that there is a wind that exerts a constant force F0 in a negative direction, negative to x. In terms of F0 and the acceleration due to gravity, at what angle above the positive x-axis must be ball launched to order to come back to the point from which it was launched? So to solve this problem we can just make a picture and see that resulting force mg and F0 is going this way. So that will be our efficient force, like efficient gravity. So we know that if we want to launch any object back to us, we need to throw it exactly opposite to this resulting force. So we need to find what is this angle. And from this picture we see that tangent of this angle equal mg over F0, and correct answer is this one. Problem number 25. Find the period of small oscillations of water pogo, which is a stick of mass m in the shape of box, rectangular parallelepiped. The stick has a length L and width W and height H, and is bobbing up and down in water of density ρ. Assume that the water pogo is oriented such that the length L and the width W are horizontal at all times. Assume that all equilibrium the pogo is floating. So to solve this problem we just need to write equations. What is the force when we move this box a little bit down on distance x. So we can write equation right away. Ma equal, so we have Archimedes force which is going up, so it's negative compared to displacement, and Archimedes force equal to weight of displaced water, which is rho L W X G. So this is our equation for motion. We can rewrite it in form of A equal negative rho L W G over M X. We see that acceleration proportional to displacement and always going back to displacement. That's a regular equation for simple harmonic motion, and we know that in this case this coefficient is exactly omega square. So we have, from this we have period equal to pi root of m over rho L W G. So this is the answer. Here we have from the left side we have many different answers, but correct answer is D, this one. Problem number 26. A sled loaded with the children starts from rest and slides down a snowy 25 degrees with respect to horizontal incline, traveling 85 meters in 17 seconds. Ignore high resistance. What is the coefficient of kinetic friction between the sled and the slope? If we know what is acceleration, we can find what is coefficient of friction, because we have this equation Ma equal horizontal part of gravity force, which is mg sine alpha, minus force of friction, which is mu, multiplied by normal force, which is mg cosine alpha. So from here we can find what is acceleration. That's a g sine alpha minus mu cosine alpha. So from this formula we can find what is coefficient of friction if we know what is acceleration. Alpha is done, 25 degrees. But acceleration we can find from this data. We have distance, we have time, and we have kinematic formula that distance equal 1/2 a t square, and we can find that acceleration equal 2d over t square. All numbers are done, and we can count what is acceleration, put in this formula, and find what is the coefficient of friction. That will be 0.4. Problems number from 28 to 30. We have 3 problems in a row which are connected to the same picture. So first problem. We have a simplified model of a bicycle of mass m. Has two tires that each comes into contact with the ground at a point. The wheelbase of this bicycle, the distance between the points of contact with the ground is W. And the center of mass of the bicycle is located midway between the tires and the height h above the ground. The bicycle is moving to the right, but slowing down at a constant rate. We can say it's a. Acceleration has a magnitude a. Resistance may be neglectable, ignored. So first case, number 28. Assume that the coefficient of sliding friction between each tires and the ground is mu, and that both tires are skidding, sliding without rotating. Express your answer in terms of W, H, M and G. What is the maximum value of mu so that both tires remains in contact with the ground? So if we have this situation that both tires contact with the ground and the acceleration is a, it's the easiest way to solve this problem to go to frame of reference of this bicycle. If we have a deceleration to the left in this frame, we have effective gravity field A to the right. And in case if both tires are in contact, it means that this tire has a normal force N1 and this N2. This N1 is 0 and this N2 equal to total weight of whole bicycle with the bicyclist. So in this frame of reference we just need to write equation for static equilibrium around point of contact, point of rotation. So maximum possible acceleration could be if we have a sliding case. It means that this force equal mu mg, and this force create a torque around this point equal mu mgh, which is rotating our picture to the right, clockwise. And we have torque created by force of gravity, which is mg multiplied by w over 2, which is going counterclockwise. So from this equation we can find that the maximum possible coefficient of friction equal w over 2h. And if we look at this answers, the correct answer is A. Next problem, number 29. We have the same setup. What is the maximum value of A, acceleration A, so that both tires remain in contact with the ground? So now best way to use our original frame of reference, in which we have force of friction F1, force of friction F2, and we have normal forces N1 and N2. and we will choose rotation around center of mass to exclude gravity force. So if you look at this picture, we have three forces which are acting clockwise around center of mass, which is F1, F2 and N1, and the force N2 acting counterclockwise. So first we can write equation F1 plus F2, that's equal MA, and the equation for static rotation we have F1 plus F2 multiplied by H plus N1 multiplied by W over 2, that's equal N2 multiplied by W over 2. So now we can put F1 plus F2 equal MA here. So we have MHA equal N2 minus N1 multiplied by W over 2. And finally we have acceleration A equal N2 minus N1 over M W over 2H. So if you look at this equation, we have N1 minus N2, but we know that N1 plus N2, that's equal mg. So, and it means that maximum acceleration we can get when N1 equals 0. In that case N2 equal mg, and then finally we have wg over 2h. That's answer B. Problem number 30. Assume that both tires are skidding, sliding without rotating. What is the maximum value of A so that both tires remain in contact with the ground? Correct answer is the same as for problem number 29, because in that previous problem it doesn't matter. It was sliding or rotating, so we found the maximum possible acceleration for any condition. So it means that the answer is the same, but we don't see this answer here, so the correct answer is none of them. Problems number 31 to 33. We have thin uniform thin rod has mass m and length l. Let the acceleration due to gravity is g. Let the rotational inertia of the rod about its center is I equal md square. So first problem number 31. Find the ratio L over D. So this problem we can solve if we know that moment of inertia equal 1 over 12 m L square, which is equal md square, and from here we see that L over D equal root from 12, which is 2 root 3, and correct answer is D. Problem number 32. Now the rod is suspended from point at distance kd from the center. This point, this distance kd, and undergoes small oscillations with the angular frequency omega equal beta root g over d. We need to find what is beta, coefficient beta, in terms of k. So to solve this problem we need to write equation for rotation around this point. For rotation we have formula that I alpha equal negative force, which is mg, multiplied by level arm, which is kd multiplied by sine theta. Kd multiplied by sine theta. So for small oscillations we assume that sine theta approximately equal theta. To count what is I around point on distance kd, we can use parallel axis theorem, from which we have I equal md square, that's I0, plus mkd square. And finally rewrite this equation in form of md square plus mkd square multiplied by alpha equal negative mg kd theta. This part we can move to the right, and we have alpha equal negative k over 1 plus k square g over d theta. If you look at this equation, that's exactly an equation for small harmonic oscillation. In that case, this coefficient exactly equal to omega square, and we can write omega equal root k over 1 plus k square root g over d. And finally this is our coefficient beta, which is none of them. Correct answer is E. Problem number 33. In previous problem we found what is a coefficient beta. In this problem we need to find what is a maximum for this coefficient. So to find the maximum for this function we need to find maximum for function k over 1 plus k square, or to faster solve this problem we need to find, we can flip this function and find minimum for this function. We need to take first derivative for that, that's 1 minus 1 over k square, and equalize it to 0, so which is k equal 1 and beta equal 1 over root 2, which is C. Correct answer. Problem numbers 34 till 36. We have point object of mass m is connected to a cylinder of radius r via a massless rope. At time t0 the object is moving with the initial velocity v0 perpendicular to the rope. The rope has length L0 and the rope has a non-zero tension. All motion occurs on a horizontal frictionless surface. The cylinder remains stationary on the surface and does not rotate. The object moves in such a way that the rope slowly winds up around the cylinder. The rope will break when the tension exceeds T maximum. Express your answer in these parameters. First question. What is the angular momentum of the object with respect to the axis of the cylinder at the instant when the rope breaks? This is question number 34. Question number 35. What is the kinetic energy of the object at the instant that the rope breaks? That's question number 35. And question number 36. What is the length, not yet wound, of the rope in this moment? Yes. So, to solve these problems, we can go 34, 36, 34, 35, 36, 34. So first of all, we have tension always perpendicular to motion. It means that speed remains the same, constant. It means that kinetic energy equal 1/2 mv0 square. This is answer for 35. Next one, we have tension, maximum possible tension is Tm, and we can write the equation that Tm equal mv0 square over r. So that's minimum possible r. So from here we can find that r for brake it's equal to mv0 square over T maximum. That's the answer for 36. And for 34 we have L equal mass multiplied by speed, which is constant, and multiplied by a level arm. In our case that will be exactly r counted here, because velocity is perpendicular to this vector, and we know that we have L equal momentum cross product with a level arm. So we need to put here r. It's mv0 square over T maximum, and total answer is m square v0 cube over T maximum. So that's answer for 34. Problem number 37 and 38. That's the last problems for this competition. First problem from these two problems is looks like this. Massless elastic cord that obeys Hooke's law will break if the tension in the cord exceeds T maximum, unknown tension. One end of the cord is attached to a fixed point. The other is attached to an object of mass 3m. If a second smaller object of mass m moving at an initial speed v0, the larger mass and the two stick together, the cord will stretch and break, but the final kinetic energy of the two masses will be zero, so they will stop after break. If instead the two collide with a perfectly elastic one-dimensional collision, the cord will still break and the larger mass will move off with the initial speed of Vf. So we have F0, V final, we have object mass m, and we have object mass 3m. All motions occurs on a horizontal frictionless surface. So first question is, that's problem number 37. What is the ratio between V final and the V initial? So to solve this problem we need to do several steps. So first step is we have information that this cord will break for certain tension Tm, and it's a Bay-Hook law. It means that it will get some potential energy, and for this energy it will break. So in any case, if it will break, we are losing some certain amount of energy, and we can count what is this energy, because when these two masses have absolutely inelastic collision, it means that we can use momentum conservation and find what is new speed after they will stick together. So new speed will be 1/4 from initial speed of the first mass. After that we can count what is total kinetic energy after this collision, and all this energy will go to a potential energy for this cord before it will break. So it means that all this energy, K, equal 1/2 4 m multiplied by 1/4 V0 square, which is 1/8 m V0 square. So we have this information about maximum possible potential energy for this cord, which we can use in a second step. So second step, we have absolutely elastic collision for two masses. One is moving and other is not moving. Good idea to know final formulas, just to memorize these final formulas, because we can use in many problems these formulas. What are the velocities for these masses after collision, after perfect elastic collision? This formula looks like this. V1 for the first mass, we have velocity is m1 minus m2 over m1 plus m2 v0, and v2 equal, for the second mass, that's equal to m1 over m1 plus m2 v0. But if you don't remember these formulas, you can do very quick calculations to find them. Of course we can use momentum conservation and energy conservation laws to find these velocities, but it's a long way. The shortcut is to use new frame of reference, frame of reference for center of mass, and check what happened in this system. In this system, if we have two masses and immovable center of mass, they will go to this center of mass, collide here, and just rebound with the same speed, because we don't lose energy. So we just flip velocities. And after that we can go back to our initial frame of reference. Let's see. The velocity of this frame reference, v center of mass, that's equal, using momentum conservation, that will be m1 over m1 plus m2 v0. In this system, second mass moving to the left with this same velocity, but after collision it will change direction and it will go to the right with the same velocity. And when we are going back to our initial frame of reference, we just need to add to this new speed, new velocity, velocity of the center of mass, which is the same. So we have v2 equal to m1 over m1 plus m2 v0. For the first mass, we have speed, velocity in the center of mass will be v0 minus m1 over m1 plus m2 v0. That's a velocity of this first mass in the center of mass. After that it will flip, it will be negative, and we are going back to our initial frame of reference. We need to add the velocity of the center of mass, m1 over m1 plus m2 v0, which is finally equal m1 minus m2 over m1 plus m2 v0. So that's this one. Now we can use these formulas to count what is the speed, what is the velocity of this second mass after collision. We have v2 equal 2m1, which is m, over m plus 3m v0, which is 1/2 v0. That's the speed of our second mass. And we can count what is total kinetic energy of this mass. K2 equal 1/2 3m 1/2 v0 square, which is equal what is it, 3 over 8 m v0 square. Okay, that's a kinetic energy right after collision. But when it will go with the cord, we extend the cord will get some potential energy before it breaks. And we know what is the potential energy for break, so we need to just to subtract this energy. So that's a 1 over 8 m v0 square, which is 1 over 4 m v0 square. That's our kinetic energy after break for the second mass. And now we can find what is final speed of this mass. That will be 1/2 3m over v final square, which is equal 1 over 4 m v0 square. So now we see that v final equal 1 over root 6 v0, which is answer C, correct answer. Problem number 38. Find the ratio of the total kinetic energy of the system of two masses after the perfectly elastic collision and the cord has broken to the initial kinetic energy of the smallest mass prior to the collision. So we need to find what is K2, final kinetic energy, to initial kinetic energy. So from the first problem we already found how much energy do we lose for a cord break, this potential energy. That was P equal 1/8 mv0 square. And the initial kinetic energy K1 was 1/2 mv0 square. So to find what is K2, we just need to subtract from K1 losing potential energy, which is 3/8 mv0 square, and finally K2 over K1 equal 3/4, which is answer D.